In Lecture 9, we will cover the design of one-way slabs. To give you background information on the design of slabs, well, in reinforced concrete buildings, the floor system consists of slabs which receive the loads. These loads are then transmitted to the beams. The beams transmit the load to the columns. Then the columns transmit these loads to the foundations. And finally, when it gets to the foundation, then these loads are transmitted safely to the ground. There are 5 types of RC slabs, the main one being solid slabs. Solid slabs, like the one shown in the picture, are used for short to medium spans of about 6 meters. The slabs may be supported on walls or beams. The beams could be downstand or upstand. Solid slabs can achieve cantilever spans of about 3 meters with beams or 1.5 meters if the slab cantilevers without the support of beams. The second type of RC slabs are ribbed slabs. Ribbed slabs are used for long spans, generally from 6 to 12 meters. The spaces in between the ribs may be used or may be filled with lightweight hollow clay or concrete pots to reduce formwork costs and to achieve a flat ceiling. The system is then referred to as a hollow pot slab system. The hollow pots may be fit inside these ribs. They're usually hollow so that they become light. The next slide will show us an example where hollow clay pots are used. In this picture, we can see hollow clay pots being put on formwork before concrete is poured. Here, we can see how the ribs are achieved before the reinforcement is placed and the concrete poured to achieve a ribbed slab as shown in this schematic. The third type of RC slabs are called waffle slabs. These are ribbed slabs where the ribs run in both directions. An example where you can see a ribbed slab is the civil block at the University of Nairobi. In a waffle slab, as you can see in the picture, the ribs run in perpendicular directions. The fourth type of slabs are stair slabs. These are slabs which are designed to facilitate elevation from one level to another. Stair slabs could be linear or spiral. The fifth type of slab are ramp slabs. These are similar to stairs and facilitate elevation from one level to another. Ramp slabs are adopted when designing for movement of objects with wheels, such as in a parking silo for motor vehicles, hospitals so that they can accommodate stretchers, or in normal buildings to cater for people with disabilities. Stair slabs can be further categorized into 3. The first one being stairs spanning transversely. This is where the supports are on 2 sides of a particular stair, or whether the stair is cantilevered off the support. The second category of stair slabs are stairs spanning longitudinally. In this case, the support is on the end of the staircase flight and on the other end of the staircase flight. The third category of stair slabs are spiral stairs. These are stairs that spiral around a central column, or they could be freestanding. Slabs are designed as one-way spanning slabs. The dead loads are calculated along the plan, and the live loads are calculated on plan. Our main focus for this design class will be solid slabs. So we'll circle back to the first type of RC slabs. Depending on the geometry and arrangement of supports, solid slabs may be classified into three categories: one-way spanning slabs, two-way spanning slabs, or complex slabs. In general, one-way and two-way spanning slabs are rectangular in plan with symmetric support arrangement. Complex slabs deviate from the simple geometry of a rectangle, or their supports do not show it. We shall limit our discussion to one-way and two-way slabs only. Let us look at the difference between one-way and two-way slabs. So, if a rectangular slab is supported on only two opposite sides, then the slab is considered one-way spanning. Similarly, if a rectangular slab is cantilevered from one side only, then it is one-way spanning. If a slab is supported on all four sides, we'll have an additional check. We'll have to look at the ratio of the longer side to the shorter side. If the ratio of the longer side Ly to the shorter side Lx is less than 2, then that is considered a two-way slab. If the ratio of the longer side Ly to the shorter side Lx is greater than 2, that is considered one-way. To use figures to illustrate these 4 points, I'll make some sketches on the picture. So, for example, a slab is supported on two sides, such as in point A here, then this is considered a one-way spanning slab. This could also happen in the other direction if the supports are in this direction and this other side. This will also be considered a one-way spanning slab. To get to point 2 then, if a rectangular slab is cantilevered from one side only, it is also considered one-way spanning slab. Look at condition B then, and we only have one support in just that direction, then that is also considered a one-way spanning slab. Then we'll go to point C. Let us consider a rectangular slab as shown, which is supported on all four sides, such as shown in the sketch. Then we'll have to do an additional check. We'll have to get Ly. Ly is always the longer side over Lx. For it to be, if it is less than 2, then it will be considered two-way. So let's look at this other sketch. Now let's assume they're all in scale and this other slab is also supported on all four sides. Ly will always be the longer side and Lx will be the shorter side. In this case, since they're almost to scale, we can actually tell that indeed Ly over Lx is less than 2, since they're almost the same. We could say here Ly over Lx is around 1. So this is actually a two-way slab. Back to our first rectangle, if you were to assume Ly is much longer than Lx such that Ly over Lx is greater than 2, this will give us a one-way spanning slab. In this case, this will be condition D and this will be condition C. Lastly, we have complex slabs. A triangle is considered a complex slab because of its differences in symmetry along different axes. The methods used to analyze slabs are based on design codes that allow the application of simplified methods to determine the critical mid-span bending moment. One-way spanning slabs are analyzed as if they were made up of beam strips each 1 meter wide. This is a sketch of our one-way spanning slab. We will take a beam strip, we'll assume a 1 meter strip, and design for that. In two-way spanning slabs, the slabs are analyzed as if they were made up of beam strips, each 1 meter wide, spanning both directions. Just to sketch again, if this was the rectangular two-way slab, we will have to design this meter strip. This is 1 meter or 1000 millimeters. We'll also assume a section in the perpendicular direction, also 1 meter. (1000 millimeters), and design that section. This particular section in green. That will be the most stressed point in our slab. The moments at this point in green are usually given by the formula MSX is equals to alpha SX eta Lx squared. So that will be the moment in that direction. And we'll need MSY as well, which will be given by alpha SY eta Lx squared, which will give us the moment in the other direction about the circled point. Please note that in all these two instances, it's only the coefficient alpha Sx and alpha Sy changing. Lx squared is used in both instances. The coefficients are given in the handout provided, and they are dependent on the ratio of Ly over Lx. They start from 1.0 all the way to 2.0. Remember, if Ly over Lx exceeds 2, then that will not be a two-way spanning slab, but a one-way spanning slab. MSX is the moment in the major direction or the moment in the shorter direction. MSY is the moment in the minor direction or in the longer direction. MSX and MSY are the maximum bending moments at the midspan of the two-way slab. Lx is the shorter direction, Ly is the longer direction. Eta is the ultimate design load per unit area, given as 1.35 GK plus 1.5 QK according to the Eurocode, where GK is the permanent action per unit area with the units kilonewton per meter squared, while QK is the variable action per unit area given in kilonewton per meter squared. Alpha Sx and alpha Sy are the moment coefficients given in the coefficients table. The moment coefficient table shown previously was for one in which the slab is simply supported by the supports. For example, think of this slab which is directly supported by walls. Showing the sketch there. So in this case, the slab is supported at the highlighted point, simply supported by the walls. 95% of the time, you will find that slabs are usually laid or poured together with beams in the manner shown. The beams could then be supported by walls, for example, as shown. In this scenario then, you can see the slab is supported by beams that have a restraining effect on the edges of the slab. To get the moments of slabs supported by such restraining beams, we have a different table to cater for all these end conditions. For example, let's consider a slab in a residential building. The lines I'm drawing indicate the beams will be straight. Then we could have additional beams so that we have different panels with different dimensions. Something of the sort. So for example, if we wanted to design, let me give them letters, labels, A, B, C, D, E, F, G, H, I. For the purpose of this example, we'll assume that the drawing has some sense of scale to it. For example, if I wanted to design panel E, then panel E is an interior panel because it has neighboring panels all around it. So panel E will be an interior panel. And I'll use the values here to determine the moments at the midspan. In a second scenario where I have one short edge discontinuous, I'll think of, say, panel F, where this side is longer than this, but those sides have adjacent panels next to it. So it's only on this side, which I've marked with an X, which is discontinuous. So in the case, I would like to get the moments in panel F, I'll have to read the values of panel type 2 because only one short edge is discontinuous. I could also, in case I wanted to design panel, say, B, I'll find that the long edge here, which I'm marking with Y, is discontinuous, but the other panels adjacent to A is continuous, on this side of C is continuous, on this side of E is continuous. Then to get the moments in the panel B, I'll have to read that of type 3. If I wanted for panel type A, then I'll have two adjacent edges discontinuous because that is discontinuous, which I'm marking with Z, that edge which I'm marking with Z are discontinuous. Those are the only two edges that are discontinuous. The remaining two edges are continuous. So if I wanted the moment coefficients of panel A, I'll go to type 4, where there are two adjacent edges discontinuous, and so on and so forth. The tables are quite comprehensive and provide all scenarios for rectangular panels, including a scenario in which we just have a singular panel with no adjacent panels. That would be slab type 9 as shown. In this table, you need to read off beta Sx depending on your ratio of Ly over Lx, and you also need to read off beta Sy. If the slab is restrained, that is, the slab is continuous or fixed at the edges by beams, then the maximum midspan bending moments are given by Msx is equals to beta Sx multiplied by eta multiplied by Lx squared. Msx is also known as the moment in the major direction, and the major direction is usually the shorter direction. MSy is given by beta Sy times eta times Lx squared. Lx squared is repeated in both scenarios again. The only thing that changes in the two is the coefficient beta Sx and beta Sy. MSy is known as the minor direction or the moment in the longer direction. Beta Sx and beta Sy are moment coefficients given in the coefficients table for restrained slabs. Once the moments are computed, then one will find that the design principles for RC solid slabs are the same as for rectangular beams. First, one will need to calculate K, followed by Z, which is the lever arm between the resultant force, the resultant compressive force, and the resultant tensile force in the concrete cross section. Then they will calculate the area of steel required, which is MED all over 0.87 FYK multiplied by Z. In this case, B is taken as 1 meter because we were using 1 meter strips, and D is estimated as usual. M is the design ultimate bending moment per unit width expressed in kilonewton meter per meter. And S is the tensile reinforcement per unit width expressed in millimeter squared per meter and obtained from table 2 of the steel reinforcement handout areas. Some further notes in the design of reinforced concrete slabs. Solid slabs are usually under reinforced. This just means that the steel will fail before the concrete fails. This is achieved by using the formulas earlier derived. K is usually less than 0.167, and slabs are usually singly reinforced. There is no need for compression reinforcement for slabs in a residential building. Slabs in bridges may need compression reinforcement. The recommendation for nominal tensile reinforcement applies. This is taken as 0.13% BD. The area of steel is provided on the basis of the above calculations and is referred to as the main bars. And the bars are arranged in the direction of the span associated with critical bending moment. Distribution bars are then provided on the basis of the lesser bending moment or on the basis of the nominal reinforcement. The distribution bars are arranged perpendicular to the main bars, and the two sets are bound together at every intersection to form a mesh. If the slab is supported on beams or walls, the shear falls will be negligible and there is no need to carry out the checks for design or for shear that is in slabs. The verification and on deflection steel. The following three examples should reinforce our understanding. The first example will be on one-way spanning slab. The second will be on a two-way spanning slab that is unrestrained. And the third example will be a two-way slab that is restrained by beams. A 10 meter by 3.8 meter slab in an office block with fixtures and fittings of 1.16 kilonewton per meter squared. A screed of 50 millimeters will be applied on the finished structural concrete. Assume T12 main bars and a cover of 25 millimeters and an overall depth of 150 millimeters. The concrete class is C2530. The reinforcement characteristic strength is 460 MPa. So when designing this slab, we'll need first to compute the loading on the slab. The first thing we know is that this is a concrete slab, so we need to find out the density of concrete, which as provided in the handout is 24 kilonewton per meter squared. The Eurocode recommends that for reinforced concrete, an additional 1 kilonewton per meter cubic to plain concrete is added. Secondly, to compute the live loads or the occupancy loads, we have been told that this is an office block and we'll read off the value of variable action for offices, which is 2.5 kilonewton per meter squared. From the question, we will determine that the longer span Ly is 10 meters in the shorter direction, Lx is 3.8 meters. Ly over Lx will give us 2.63, which is more than 2, and therefore this is a one-way slab. To compute the loads, we'll first start with the permanent actions. Start with the self-weight of the reinforced concrete, which we had been given that the overall depth was 150 millimeters. So converting this to meters, we'll get 0.15 times the density of reinforced concrete, which is 24 plus 1, gives us 25. We'll end up with 3.75. Then the screed, which we had been given as 50 millimeters, will translate to 0.05 meters times the density of plain concrete, which is 24, and that will give us 1.2 kilonewton per meter squared. Lastly, for the permanent actions, we have been given the fixtures and fittings was 1.16 kilonewton per meter squared. We will input that directly. total it up and get the total dead load, GK, is given as 6.11. Then for the occupancy of the office, which we had read off from a handout as 2.5, will be our only variable action. So QK is equals to 2.5 kilonewton per meter squared. Then we will compute the value of the design load eta, given as 1.35 GK plus 1.5 QK, to get that eta is equals to 12 kilonewton per meter squared. So we will consider a section of the slab, if this is it. We'll consider just a single 1 meter strip, 1 meter, and we will design this 1 meter strip whose width B will now be 1000. And we have found the design load as 12 kilonewton per meter squared. So multiplying 12 kilonewton per meter squared by 1 meter, we will get the design load on this 1 meter strip is 12 kilonewton per meter. We could then idealize this as a beam whose design load is 12 kilonewton per meter. So the free body diagram will look something of this sort. The shear force diagram, which will be given in kilonewtons, will take this form. We could confirm this by computing WL over 2 to get maximum shear. And the bending moment diagram, given in kilonewton meter, will take this format. Can confirm this by inputting WL squared over 8, which will give you the moment at the midspan, which is 21.66. You will then need to calculate the effective depth, which will be given by the overall depth minus the cover minus half the main bar diameter. H will be 150, the cover will be 25, and we'll assume the main bar diameter as 12. This will give us 119. Unlike in beams, slabs in residential buildings do not have shear reinforcement. Hence, we do not have to reduce D by the effective diameter of the links. We'll then compute the design moment of resistance, MRD, using this formula which we had earlier derived, and we'll get the design moment of resistance is 59.12 kilonewton meter. The moment effect of the design load MED will be 21.66 kilonewton meters, which is less than MRD, which implies that the slab is singly reinforced. Similarly, we could calculate K, which is MED over BD squared FCK, and we will get K as this, and it's less than K prime, which is 0.167, therefore it's singly reinforced. We will then calculate Z, which is the lever arm. In this case, when we replace the figures, we'll get Z is 0.943D, and it's therefore less than 0.95D, therefore it's okay. We'll then go ahead and calculate the area of steel required using this formula, which had been earlier derived. Computing the area of steel results in 483 millimeters squared per meter. A key reminder here is that 21.66 kilonewton meter is converted back to Newton millimeter, and it will be 21.66 times 10 to power 6 Newton millimeter. Hence this times 10 to power 6. Once we compute our required reinforcement, we need to verify that it is more than the nominal reinforcement AS mean. That is given as 0.13% BD, which when we replace the value of B and D, so B, because we're working with 1 meter strip, is 1000 and D is 119, we get 155 millimeters squared per meter. So the required area of steel is more than the nominal area of steel, so we can provide then for the area of steel that was required. That was 483 millimeters squared per meter. We go to our reinforcement table. Since we are working with millimeters squared per meter, then we'll now go to table 2 instead of table 1. We provide a reinforcement configuration that is more than 483. The first option will be T10 at 150 bottom 1, which will give us 523 millimeters squared per meter. Second option will be T12 at 225, which gives us 503 millimeters squared per meter, and T8 at 100 bottom 1, which gives us 503 millimeters squared per meter. Any of the three are right answers. Provide only one in your working. It's important to note that there are some practicalities in construction. So for example, T8 at 100 will have such a tight spacing. You may not really want to include it. But some of those are nuances of construction. We need not consider them at this point. To calculate the reinforcement in the other direction, since it was one way, we'll just provide the nominal amount of reinforcement in the other direction. That is given by AS mean, which is 0.13% BD. When we compute that, we will get 155 millimeters squared per meter. From our reinforcement table, we'll provide something larger than 155, which we can see is T8 at 300 bottom 2 will give us 168 millimeters squared, which is more than 155 millimeters squared per meter. And that will be bottom 2. We could then go ahead and provide a sketch. So for example, if this was our slab, this is 3.8 meters. This was the longer side, 10 meters. I will have to provide reinforcement in the main direction. So which we had said was T8 at 300 bottom 1. Can annotate in that manner. This will give us T8 at 150 bottom 1, which gave us, sorry, this was T10. T10 at 150 bottom 1, which gave us 523 millimeters squared per meter. And in the minor direction, we shall use green to show the reinforcement. I'll have my bars in that sort of orientation. I'll just draw only one bar, otherwise my drawing will look very cluttered. Of course, you sketch this quite fast in your design calc sheet. And then this bar will run in that sort of orientation, and this will give us T8 at 300 bottom 2, which gives us 168 millimeters squared per meter. So that's a rough sketch of how your solution should be. After that, ideally we should do some shear verification. However, shear reinforcement is not provided in solid slabs of residential buildings. Since slabs have relatively big sections, hence shear is generally considered minor, unlike in beams, which has a small section for large values of loads. For slabs, we will need to calculate deflection, and it's very important. So to do that, we will use equation 716 in Eurocode 2. First, we'll need to calculate rho naught, which is our reference reinforcement ratio, which is given by this formula. Our concrete class was C2530, so we will use 25 for FCK. Our reinforcement ratio is given as the area of steel required over the cross-section area, which gives us 0.00405. And since our reinforcement ratio is less than the reference reinforcement ratio, we could use equation A. Most of the time, you will note that when you're dealing with slabs, you will end up using equation A, and when you're dealing with beams, you will end up using equation B of equation 716 of Eurocode 2. This is equation 716A reproduced here, where we'll need to calculate some of the values. Since we had assumed this was a one-way slab and simply supported, then K is equals to 1. The slab was singly reinforced, hence no compression reinforcement was required, and rho prime is 0. F1 is computed as follows. We computed we needed 483, even though we provided 523 millimeters squared per meter in the form of T10 at 150 bottom 1. It's important to note that deflection is only carried in the major direction, which happens to be the shorter direction in our slab. F1 is then computed as 1.18. Replacing all these figures in equation A, we get the limit of our span to depth is 26.05. We will then need to calculate the actual span over depth, which was 3.8 meters, since you're actually calculating deflection on the shorter span only. 3,800 millimeters over the effective depth 119, we get 31.93. In our case, since our actual span to depth ratio, which is 31.93, is greater than our span to depth limit, which was about 26, then we can see our slab is not adequate in deflection. When this happens, then we note our slab has failed our serviceability limit, and we can recommend that we can increase the slab depth or increase the tension reinforcement. We could go back to our question, and maybe instead of replacing T10 at 150 bottom 1, which gave us 523 millimeters squared per meter, you could change this and replace maybe with something higher, say T10 at 125 or T12 at 200 bottom 1, which gives you 566 millimeters squared per meter. Then you could recheck the deflection and see if that is okay. That's the end of the lecture. See you in the next one.